Today we will learn about Laplace transformation, Fourier transformation and the relation between them. Laplace transformation and Fourier transformation are important mathematical transformations that are extremely useful in the field of signal analysis. First we learn about Fourier transformation, then some of its basic properties, then the inverse Fourier transformation, then we learn about the Laplace transformation, then some of its basic properties and its inverse. Then finally we learn about the relationship between Laplace and Fourier transformation. So, first, the Fourier transformation. Fourier transformation is a mathematical transform that decomposes a function, often a function of time or a signal, into its constituent frequencies. So, and then here we have the definition of the Fourier transform. Let's say a function is given gt. Then its Fourier transform is written as capital G of f, or in this particular notation, and it is defined as follows. It's an integral from minus infinity to infinity. Then inside we have the function itself, then e to the power minus 2 pi I ft dt. Now this part, e to the power minus 2 pi I ft, is called the integral kernel. Often, especially when we are talking about signals, 2 pi if will be replaced with j omega. Since when we are talking about signals, they are decomposed into sine and cos, so we'll need the angular frequency, and angular frequency omega is equal to 2 pi f, and in angular, when we are talking about angles, usually I is replaced with j. Now some of the basic properties of Fourier transform. Linearity. Now if a function hx equals a into fx plus b into gx, here a and b can be complex numbers, then h cap epsilon, which is the Fourier transform of hx, equals a multiplied by f cap epsilon plus b multiplied by g cap epsilon. Now time shifting. If h of x equals f of x minus x naught, here x naught has to be a real number, then h cap epsilon equals e to the power minus 2 pi I x naught epsilon f cap epsilon. Frequency shifting. If hx equals 2 pi I e to the power 2 pi I x epsilon naught fx, then h cap epsilon equals f cap epsilon minus epsilon naught. Now you might see that the time shifting and the frequency shifting are clearly opposites of each other. Then time scaling. If h of x equals f of ax, here again a is a real number, then h cap epsilon naught equals 1 by modulus of a multiplied by f cap of epsilon by a. Now the inverse Fourier transformation. Now under some suitable conditions, a function f can be recovered from its Fourier transformation. In fact, for most of these invertible functions, applying the Fourier transform twice reverses the function, that is, it turns fx into f of minus x. In such cases, simply applying the Fourier transform 4 times will give us back the function. Now we'll learn about the Laplace transform. The Laplace transform is an integral transform that converts a function of a real variable t to a function of a complex variable s. In particular, it transforms differential equations into algebraic equations, and it turns convolution into multiplication. Now here we have the definition of the Laplace transform. F of s equals an integral from 0 to infinite of ft into e to the power minus st dt. Here ft is the function itself of which the Laplace transformation is being done, and e to the power minus st is the integral kernel. And here we have the definition of the bilateral Laplace transform. Fs equals minus infinity to infinity integral of e to the power minus st into ft dt. Now these two are similar, except instead of being integrated from 0 to infinity in the bilateral Laplace transformation, we integrate from minus infinity to infinity. Usually when we are talking about Laplace transformation, we talk about the unilateral Laplace transformation, the first one, but here in this presentation we'll mainly talk about the bilateral Laplace transformation. Now some of its basic properties. First, linearity. A into ft plus b into gt in the t domain becomes a into fs plus b into gs in the s domain. Here a and b are any complex numbers. Frequency shifting. U to the power at ft in the t domain becomes f of s minus a in the s domain. Here a can be a complex number. Time shifting f of t minus a into u of t minus a in the t domain becomes e raised to the power minus as into fs in the s domain. Here a has to be a real number. And finally, time scaling f of at in the t domain becomes 1 by a into f of s minus a s by a in the s domain. Here a has to be a real number. You might see the similarities between the properties of the Laplace transformation and the properties of the Fourier transformation. Now, the inverse Laplace transformation. The inverse Laplace transform of a function fs in s domain is a function ft in t domain such that Laplace of small f equals f of capital F of s. Now, the inverse Laplace transformation can be done using several methods, mainly the Mellon's inversion formula and Post's inversion formula. Post's inversion formula actually looks very simple, but it is extremely impractical to do. And now finally, we come to the relationship between Fourier and Laplace transformation. Here we have the formulas of the Fourier transform and the Laplace transforms respectively. Now, we can clearly see that the expressions look extremely similar. In addition, we will be replacing 2 pi if with j omega as we would do for a signal. This I have explained before as omega, the angular frequency, will be replaced by 2 pi f and I will be replaced by j. Now, s, the complex number, is written as sigma plus j omega. Now, putting that in the formula of bilateral Laplace transformation, we get x of s, which is replaced with omega plus j omega, equals integration from minus infinity to infinity into xt e to the power minus sigma plus j omega t dt. Now, we'll open the brackets and remove sigma t. The equation becomes minus integration of minus infinity to infinity xt into e to the power minus sigma t multiplied by e to the power minus j omega t dt. Thus, we can clearly see that this is the Fourier transform of xt into e to the power minus sigma t. Thus, we have clearly obtained a relationship, a direct conversion between the bilateral Laplace transformation and the Fourier transformation. In addition, we will note that when sigma equals 0, e to the power minus sigma t becomes 1, and thus bilateral Laplace transformation and Fourier transformation will give us the same result. Now, in s equals sigma plus j omega, sigma is the real part of s. Therefore, in a complex plane, the Laplace transformation uses the entire plane, while the Fourier transformation uses only the imaginary line. Thus, the Fourier transformation gives the imaginary part of the bilateral Laplace transformation, or we can say in a simplified manner that doing the bilateral Laplace transformation only on the imaginary line will give us the Fourier transformation. Thank you.